Okay, so just to do a short test, is it okay? Everyone is coming in the session this afternoon from track A. So it's okay, you listen to me?
Yes.
Okay, so, sorry, because I was not sure with my connection. So welcome to this track A session dedicated to air traffic management, airspace design. My name is Professor Delahaye. I'm working at the ENAC and I will be the session chair for this afternoon. So this afternoon we have 3 presentations. The first one will be given by Leonardo Caranti. I'm sorry for the pronunciation. So he's a teaching assistant at the Delft University of Technology. As a student at this university, he wrote a paper in collaboration, this paper with Marta Ribeiro, Joost Ellerbeck, and Jaco Ostra as part of this bachelor program. So I give directly the floor to Leonardo, if you listen to me. So if you can share your presentation for us.
Thank you, Daniel. Thank you very much. I will share my screen now. Well, first of all, it's very good to see you all, even though very virtually. And today I'm very delighted to present the presentation that I've carried, the research that I've carried out together under the supervision of Marta Ribeiro, Joost Ellerbroek, and Jaco Hoekstra, titled Safety Optimization of a Layered Airspace Structure with Supervised Learning. Now, in terms of the presentation today, I will go through the introduction and background, and then I will focus on the problem formulation, which then led to the methodology and the results. Right, so as most of you probably already know, the expected urban airspace traffic densities for the future see many high-frequency coordination challenges. However, existing research does advocate that higher traffic densities can be achieved through a reduction of current traffic flow constraints. This was also found in the Metropolis project, where a comparison of 4 different urban airspace architectures was carried out. One of these was the so-called layered airspace. This concept entails subdividing the airspace into many different layers, and one way to do this is based on the heading of each different aircraft. One way is to divide the whole heading range into 8 layers, like is done in this picture, and then each single aircraft can be assigned to their respective layer. Now, this was done in Metropolis with exactly 8 layers, and 2 specific advantages, 2 main advantages were found. The first one is that aircraft by default have vertical separation. In other words, aircraft can only collide or have safety issues, safety conflicts with other aircraft only in the same layer. Moreover, by default, again, aircraft tend to fly more parallel. In other words, their headings are more aligned. In turn, this does decrease relative speeds, which in turn, again, decreases the conflict rate. However, do these advantages always hold? Let's have a look at this through a couple of examples. First of all, let's take aircraft which are all uniformly distributed in heading. Let's take 8 of them just to make it simpler. And let's take a simplified, evenly distributed layers concept with 4 layers. Now, as you can see from the number of aircraft for each layer in red, on average, every layer has approximately the same number of aircraft. Intuitively, this could work. It seems like a plausible option. However, let's take a set of 8 aircraft which is not uniformly distributed. You can already see that 6 out of these 8 aircraft are between 0 and 90 degrees of heading. This is also reflected in the assignment for each layer. Some layers have very few aircraft, and some layers have many. Again, intuitively, this probably is not an optimal case. An intuitive solution for this specific example would be to revise the layer concept and to change the assignment of each layer for the respective heading. One way to do this is the following. And as you can see already, now the number of aircraft per layer is seems to be more intuitively optimal. Now, this led to the following problem formulation. Given a set of aircraft within a layered airspace, find the optimal layer assignment, which minimizes the number of conflicts. Now, due to the lack of a stochastic process in the formulation of the problem, two supervised learning neural networks were chosen as a method. The first one, defined as the conflict estimator network, has a goal to estimate the number of conflicts given a traffic scenario. And in the training, the estimation is compared to an actual simulation of the true number of conflicts. I will talk about that later on the simulation itself. The second neural network, the layer heading network, has a goal as to assign aircraft to layers while minimizing the overall estimated number of conflicts. Intuitively, it can be seen how these two neural networks could work in tandem to produce an optimal result. In order to evaluate conflicts in a more realistic setting, a conflict resolution method was chosen, and the chosen one was the modified voltage potential. This algorithm takes inspiration from the repulsion of charged particles to attempt to minimize the path deviation when two aircraft have a conflict in the resolution of the conflict. Here you can see, or at least I hope you can see, how the modified voltage potential works. And as you can see, the aircraft do divert their paths in such a way to avoid incoming aircraft, but not in a drastic way. In terms of the training environment, you can see on the right the geometrics, the geometry. The departure bound for the departure coordinates of the aircraft was shown in green, while all the arrival coordinates were set between the two red lines. Moreover, the actual loss functions for every one of the two neural networks were defined as follows. For the conflict estimator network, the loss function was chosen as the mean squared error between the actual number of conflicts and the estimated number of conflicts. On the other hand, for the layer heading network, the loss was directly the number of estimated conflicts. And for both neural networks, the same number of aircraft and the same number of layers was used, merely 108 respectively. As I have previously mentioned, in order to obtain the true number of conflicts, a simulation was used with the Blue Sky, with the open air traffic simulator. This tool has a airborne separation and assurance system to which many different conflict detection resolution algorithms can be applied. This does allow for them to be tested under the same conditions, if one would want to. Now, in terms of the results, let's start with the training of the conflict estimator network. As you can see from this graph, which shows the difference between the actual and the estimated number of conflicts, the neural network does appear to learn a pattern because this difference does decrease. The episodes were terminated once the moving average did not improve for more than 30 episodes. And even though 300 episodes does seem limited, this was the limiting factor was the computational time, which was 36 hours on my laptop. On the other hand, for the other neural network, the computational cost was significantly lower, so more episodes were run. And again, you can see how the layer heading network appears to be able to find a pattern to minimize the number of conflicts. However, let's take an example to exactly see how the neural networks approach the problem. This is the aircraft distribution for a random example. the aircraft are separated into bins, exactly 12 bins, and I'm going to take one to take one on the left, the one on the leftmost part to really explain this. So between 0 and 30 degrees of heading, there appear to be 7 aircraft, and so on for the other bins. This is the input to the neural networks. Then the layer heading network assigns the following 8 layers. Every one of these bars represents a layer. From this graph, one can already see a pattern. For the headings for which originally there were very low number of aircraft, for example, one can see around 250 degrees, there appear the neural network appears to assign these very large bars which are very low, and the opposite is also true. What does this mean? This means that there is a trade-off between number of aircraft in each layer and the heading range per layer. In other words, there are either many aircraft which are flying nearly parallel or very few aircraft. On the other hand, the original model from Metropolis, the evenly distributed layers, assigns the following layers. One can already notice how, since it is evenly distributed, the bins have a constant 45-degree width. And one can also notice how there are significantly more aircraft for certain layers and significantly less aircraft for others. Let's really see if the adaptive layer assignment performs better. One parameter which was evaluated was safety. Let's start with the number of conflicts, and it is important to note that this was tested under 3 different demand scenarios: low, 50 aircraft; medium, 100 aircraft, which was the demand scenario on which the networks were trained on, and high demand scenario, 150 aircraft. And already from this graph, one can see that the number of conflicts for the evenly distributed layers is significantly higher, and it does appear to and the adaptive layers seem to perform better. I would like to point out how the y-axis is logarithmic, so the difference are even more pronounced. A similar conclusion was drawn from the losses of separation for the simulations. And by looking at these 2 graphs, another conclusion on the behavior, on the emergent behavior of the algorithms was taken, which I will explain with this slide. Basically, in this slide, we compare an adaptive layer distribution without conflict resolution, so with aircraft flying straight from origin to destination, to evenly distributed layers with the conflict resolution algorithm. And one can already see that only without the conflict resolution algorithm, the adaptive layer distribution has less losses of separations. The most interesting, arguably the most interesting part of this graph is to do with the tail of the distribution. The evenly distributed layers concept has a significantly longer tail, which means that there are a number of episodes for which there are these conflict hotspots, which generate many, many losses of separation. This does not happen in the adaptive layer distribution. Another parameter which was evaluated, which was another performance indicator which was looked at, was efficiency. And one of the performance indicators within efficiency was number of landings. Now, since the episode duration was always the same, the time to arrive at the destination was how that scales is comparable to the number of landings. So this was chosen as a performance indicator. And one can see that regardless of the demand scenario, the adaptive layers seem to have approximately the same number of landings within a certain amount of time, while the performance of the evenly distributed layers appears to decrease. Finally, another performance indicator which was evaluated was the total distance, traveled. However, there was no significant difference, and this was probably because the resolution algorithm had less impact on this than landings in terms of overall efficiency. Now, what have we learned from this? Machine learning is a valid method to analyze the emergent behavior of an environment, such as an adaptive layered airspace. Moreover, the airspace structure can lower conflicts, but it is very, very dependent on the traffic demand. Supervised learning and an adaptive layered airspace, for this example, can aid this adaptation. Finally, multi-conflict situations like conflict hotspots are a challenge and will always be a challenge. However, prevention can be a solution. In terms of future work, there are 3 significant recommendations. First of all, a varying number of layers, so not set to 8 or just not set to a specific number, would be very, very interesting because this would allow one more dimension of flexibility to the demand scenario. Moreover, nonlinear trajectories of aircraft would be also a very interesting argument to dive into, simply because it is a more accurate representation of reality at some points. Finally, the goal of the neural networks in this experiment was only to minimize safety. Sorry, to minimize the number of conflicts. And as such, more complex goals could be defined to, for example, also attempt to improve efficiency in parallel, for example. Well, thank you very much. I hope you really enjoyed my presentation. And let's open the floor, or maybe better, open the chat for any questions which you might have.
Thank you very much, Leonardo. Are there any questions from the audience? Sorry, I'm not connecting with Wi-Fi, so Bram will.
I'm quickly checking, Daniel, but I don't see any questions in the Q&A in Wova. So everyone, if you would like to pose a question, go to Wova and ask your question in the Q&A section.
Perhaps people are like me, not so familiar with these things.
Feel free.
No?
I'm sorry. Yes, I do see Milan with a hand raised in Zoom.
I don't see, but feel free, Milan. I don't know who you are, but try if you.
But
ask Bram, you can help us for this.
Yes, he will be able to speak right now.
Oh, okay, good. Yes, it is even better.
Can I speak or not?
Yes.
You
Do you hear me? Do you hear me? Nice presentation, but it's not easy to understand the purpose of that in the practical sense. How it's going to be in practice, because you are insisting in resolving the conflicts, but the system is designed not to allow too many conflicts. What is the purpose of all this approach? Probably you could illustrate that with more concrete case, rather than presenting that in the very abstract sense, which is actually not easy, frankly speaking, to understand.
Yeah, thank you for your question. I will repeat it just to see if I have understood it correctly. So how would this actually help the application of
practice?
Yes. Yeah, in practice. Well, I would have to note that this project did derive from an urban airspace background. So that was the initial intent, but I tried to make it in such a way that certain conclusion can be both drawn for urban airspace and more in general air traffic management. However, in terms of practice, I think in terms of the urban airspace, when we have very, very densely trafficated situations, I think this approach would definitely help in choosing at which altitude UAVs, for example, could be assigned. And yeah, so in practice, I think this approach would definitely help very densely trafficated areas where the frequency of coordination is too high for for the current is too high to use other methods.
You mentioned urban traffic area, as I guess. So which kind of aircraft are supposed to be there?
That's a very good question, actually, because and that is why no, that's really a good question, because that's also an unknown for, I think, until we actually get
so you are going very far in front of time, in the very far future, or moderately far future.
Well, that is not up to me, but but I guess that one could draw that conclusion. However, in this paper, we have gone around this problem by replicating the same densities with aircraft with which we know the performance of. So essentially, in the model, we have scaled up this airspace, and we used I think if you look in the paper, I think I used 737s, but the dimensions were scaled up in such a way that the assumptions taken were still valid for an urban airspace. So it's only a matter of keeping the same density and keeping the same assumptions, that the conclusions drawn can be the same. I hope that answers your question.
Thank you very much.
Thank you for your question.
I see another one other, and on Key J. I don't know who you are, but Remy, could you give the floor to Key J? Yes.
Oh yes, hello. Yeah, I'm sorry. I see that my Zoom took my just credentials. Well, hello. My name is Karol Getz. I'm from Winsland Limited. We are UK-based company, and we do consultancy and research and development. And I really liked your presentation. What I could see, the use of your work, where I could see the use of your work is quite near future, because, for example, planes right now, or aircraft and flights are in many countries are already directed or controlled by data link. And for me, your work is another step to automatization of air traffic control. So were you thinking also about like the real airspace use, not only the urban drone stuff, which is quite, as Milan said, that's quite not nearly near future. That's like a little bit further future. So can you see use of your project and your work in nowadays airspace?
Well, thank you for your question and for your compliments as well. The short answer is yes. And the reason why you can probably also, you can also see it from the setup of the paper, probably, because already the choice of not very explicitly specifying urban airspace allows this transition and allows for the conclusions to be drawn for both scenarios. So the bottom line is yes. I think one could use it. One could take the conclusions and develop them and implement them also in contexts outside of urban airspace. But yes, like the reason why I delved on it was also the answer to the previous question. But I do not want to shine light only on one direction. Of course, I hope that with this answer, both worlds have been touched upon.
Are there any other questions from the audience? I have just a short one about the impact on the, I don't know if it is energy or not fuel, but the impact on the consumption of energy when you decide to assign such amount of aircraft or drone and such a layer and so on with the other.
Sorry, do you mind just a little bit?
You listen to me?
Yes, I can.
Okay, sorry, because I listened. Okay, you understand my question? So, because I see the efficiency in terms of conflict, it's okay. In terms of arriving time, it is the same. But if you fly lower or higher, you have a cost somewhere, no?
Thank you for your question. It is a good question, because in the case of applying it to the current airspace, that would be yeah, a significant aspect to take into account. Yeah, it's not a minor coordination aspect, but it is in our paper. It was beyond the scope of the paper. It's definitely recommended for the future if one would want to apply it to that sector. In the case of drones, however, the difference in density between the different altitudes of an urban airspace are not expected to be drastically different. So also the costs and the challenges are expected to be a bit minor. That being said, there could be still costs and fuel efficiencies to take into account, but the impact on those is expected to be lower for an urban airspace.
Okay. No other question? So I thank you very much, Leonardo, for this nice presentation. And I was happy because I was working for a while in Metropolis a long time ago with Jaco. So I see there are still some developments in this area. And I propose to shift to the next presenter. So I have some time left, but I will keep some time to present the next presenter. So the next one will be Florencia Lema. She's a R&D ATM engineer at the CRIDA in Spain. And she has participating in several SESAR and in-air projects with the aim of improving ATM system productivities and efficiencies. After a solid academic preparation as aerospace engineer at the Technical University of Madrid, the Politecnico di Torino, and Isale Superaero, not far from ENAC, where I am, that is why I noticed. She initiated a professional career at Toulouse, working at the Airbus A320 family program. And now she's back to study, if I can say, because she involves a master in air transportation system in parallel with involvement in CRIDA. And she will give a talk about the optimal dynamic airspace configuration based on state task network. So, Florencia, it is up to you.
Good afternoon, Daniel. Thank you for your presentation, and good afternoon to all the attendees. Let me share my screen. Okay. So the research I'm going to present is related to airspace allocation. As you may know, one of the main research areas within SESAR projects. The title of our paper is Optimal Dynamic Airspace Configuration based on State Task Networks. Here we have Madrid ACC area. This airspace is characterized by high levels of air traffic demand, and it's also a high complexity environment. The configuration of this area is done nowadays by the use of predefined elementary sectors, with an exception in Zamora area, where we have a vertical shareable airspace block. Our goal is to increase the flexibility of the configuration of this airspace. And for that purpose, we proposed to implement dynamic airspace configuration in Madrid ACC and combine it with state task networks optimization. Dynamic airspace configuration is a concept that enables a more flexible sectors configuration capable to adapt to air traffic demand. It considers the creation of multiple smaller airspace volumes that can be combined with each other in order to create these sectors configurations. These airspace volumes are the following. First, we have elementary sectors, which are 3D HCC workable sectors that cannot be split into smaller workable sectors. Then we have shareable airspace blocks, which are non-controllable sectors that need to be attached to any adjacent elementary sector in order to become controllable. And finally, our third volume, which are vertical shareable airspace blocks, are a similar concept to the previous one, but in the vertical plane, and they usually covers from 1,000 to 4,000 feet. To implement dynamic airspace configuration in Madrid ACC, We make horizontal and vertical cuts to the current sectorization. With the horizontal cuts, as we see in this figure, we obtain shareable airspace blocks and elementary sectors. The boundaries of these sectors were slightly modified to adapt them to the free route traffic sample we used. Um, the consideration of a free route airspace environment was due to the fact that the AC concept will start to be deployed at ICAC level in 2025, and by that date, free route operations will already be deployed. For the vertical cuts, we propose 4 cuts at 4 different flight levels, generating 3 vertical shareable airspace blocks, instead of the one single cut we have nowadays at flight level 3, 4, 5. In global, after applying all horizontal and vertical cuts, we obtained 20 and 28 elementary sectors, 20 shareable airspace blocks, and 72 vertical shareable airspace blocks, which make a total of 120 building blocks. In particular, in our paper, we are going to focus on this area highlighted in red. It's characterized by a high air traffic density and complexity peaks. The objective will be to find the optimal configuration plan for this area. Nowadays, with the sectorization we have, there are 12 potential configured sectors to form the configuration for this area. But with our approach, this number ascends to 290, which make it not possible for a human being to find the optimal configuration. For this reason, to tackle the large-scale optimization problem, we use state task networks. This methodology was introduced by Condili, and it's commonly used in the chemical industry for scheduling multipurpose batch process. The networks are built with interconnected nodes that represent different entities. First, we have the states, which are the circles in this diagram and represent inputs and products of material. And then we have tasks, which are the rectangles and represent the actions we need to take to transform materials from one state to another. The main advantage of this methodology is that it enables to have a simple representation of a flow sheet. The objective would be to define the value of binary variables, which are the tasks, to optimally transform material from one state to another. We use state task network methodology because it allowed a simple representation of the interconnected elements present in the AC concept. And also, after a literature review, we saw that it would be a novel approach to address the AC problem. The model we created has 3 different layers. The first one is a single feed layer of initial states, which in our case represent the air traffic demand. This layer is connected to a second one of tasks, which in our case represent the configure sectors. And then we have a third final layer with a final state, which in our case would be the controlled air traffic demand. The objective of our optimization would be to find the optimal allocation of all units, building blocks in our case, to each configured sector in order to pass the air traffic demand from its initial to its final state. The constraints imposed for our model are the following. First, we have a building block simultaneity constraint, which guarantees that if we have a configured sector containing one building block, there is not in the same configuration another configured sector containing the same building block. This constraint avoids overlaps from happening. Then we have a second constraint related to building blocks allocation. If we have an airspace divided in several building blocks and we start creating the configured sectors to form the configuration, we can encounter this situation in which there is one building block that is not allocated to any configured sector. This cannot happen because it would create gaps in our airspace, and this constraint prevents this from happening. The third constraint is related to the number of configured sectors that can be open at the same time. Sometimes we have human resources limitation in ATC service. So this constraint allows to limit the number of configured sectors that can form a configuration. And then the fourth constraint, which is related to capacity, and it limits the use of configured sectors that exceed their capacity threshold in terms of entry counts. This constraint is the only one that could be violated in case the algorithm doesn't find any solution in which all configured sectors respect this constraint. These approaches are problem to a more real situation when sometimes capacity thresholds are exceeded if there is no other option and also always under controlled circumstances. Then to build the rank of configurations, we made a cost function. First, we computed a cost that will be associated to each configure sector and is the parameter that the optimizer will use to rank all the possible configurations. The metric used to compute this cost is occupancy counts because they are directly related to controller's workload. In particular, we took integral steps of 5 minutes and sliding windows of 1 minute. The equation to obtain the cost for each configured sector is a weighted sum of two terms. First, we have the overload area in bright red in this figure that represent excess of a controller's workload. And then we have the underload area in light red that represent low levels of controller's workload. The objective would be to minimize both areas, but we'll always give more weight in this equation to the overload area because we consider it more safety critical. Finally, to obtain the cost of a configuration, we'll need to sum the cost of all the configured sectors for a minute. So in global, our algorithm takes all the configured sectors they are in the airspace, compute the cost of each of them based on occupancy counts. Then it makes all the possible combinations they are respecting the constraints imposed to obtain the list of configurations. And then it makes the rank, it orders this list according to the cost of each configuration. The results obtained are the following. We tested our framework with different dates of the summer of 2019. This period is of very high levels of air traffic demand in the Spain area. But we decided to show the results of the 21st of July. That's because this is a busy day in terms of air traffic levels and sectors overloads. In particular, we are going to show the results obtained from 6 a.m. to 9 a.m. This period contains the highest peak of traffic of complexity of that day, followed by a significant decrease of inner traffic demand. We will compare two different scenarios. Reference scenario represents current sectorization of Madrid ACC, slightly modified to adapt it to free route traffic sample, and the configuration plan that was actually opened that day. And then we have solution scenario, which represents the configuration plan proposed by our framework with the implementation of the AC concept to Madrid ACC. For the airspace under study and for the results we are going to present, we have 60 building blocks under logical and spatially ordered association led to the creation of 290 configured sectors. The results obtained are the following. We remark that for both scenarios, results adhere to demand tendency, meaning that the number of configured sectors is reduced as air traffic demand is also reduced. But we see that for solution scenario, the number of sectors for the third period from 8 a.m. to 9 a.m. is reduced by 1. And this is always desirable in ATC because it means that we'll need less human resources to control the same airspace. Then we have here a distribution of occupancy counts for both reference and solution configurations, in this case from 6 a.m. to 7 a.m. We see how for solution configuration, we have less peaks and troughs, and also that controller's workload was balanced. This balance was also represented by the computation of the standard deviation. We observe how the dispersion for reference scenario is always greater than for solution scenario. And finally, I'd like to present the graphical representation of the configuration plan obtained for the solution scenario. We have three different configurations. The first one is formed by 6 configure sectors, and we go from this one to one configuration with 5 configure sectors. In this case, we see how the lower levels of the airspace are merged into just one configure sector, covering flight level from 245 to 325. And then in the third configuration, we reduce the number of configure sectors to 4, but in this case, it's Bilbao area that merges into just one configure sector covering all flight levels. The conclusions extracted from our work are the following. First, we implemented the AC concept to Madrid ACC area. Then we applied state-task networks methodology to model the DAC problem we encountered. Then we solved the large-scale optimization problem obtained by the creation of a configuration plan for a defined time interval and airspace based on occupancy counts metrics. And the results obtained show how controlled workload is balanced, and sometimes the number of configured sectors required is also reduced. Even though here we just show the results obtained for a determined time interval and a selected date, we saw the same tendency in the results for the whole day and for the other days tested too. And finally, as future work, we proposed 2 lines of research. The first one would be to include the previous states of the airspace configuration in the modeling process in order to avoid unnecessary configuration changes. And the second one would be to include also other variables for cost calculation. We used occupancy counts, but other variables such as complexity metrics or air traffic density or uniformity could be also used to have a complete, a better estimation of the cost for each configured sector. Thank you for attending and listening to my presentation, and I'm glad to answer any questions you may have.
Thank you, Florencia, for this nice presentation. And are there some, sorry, I see, so there are some questions. Florencia, I don't know who, perhaps you will help me, perhaps, but I ask you already the question. Florencia, do you consider uncertainty in your research, or do you assume that the prediction of the best current assumption and then recalculate the best block allocation as prediction evolve? So I don't know who write to this question.
Sebastian Van Wyk?
Yes, correctly,
maybe?
Sebastian.
Okay, thanks.
Hi. Thank you for your question. So yes, in fact, our dynamic airspace configuration is always based in the predictions you have of the air traffic demand. So if this prediction is improved, obviously we could use this new prediction to run again the algorithm and then have best block allocation with the new prediction. Yes, but will always be connected or dependent on this air traffic estimation.
Another question from Moiwa. Is the capacity constraint a function of, say, the size of the sector, its altitude coverage, or any other parameters? I don't know.
And this question is
Okay,
asked by Adriana.
Adriana.
Yes,
sorry.
Adriana. Okay. Thank you for your question. In fact, this paper, presents a configuration plan optimizer that was used in PJ9 solution 44. Okay, so it's part of a SESAR project. And in this case, for the capacity threshold, we compute them with a methodology developed by NIRE, which considers like a historic workload of all the sectors, and try to estimate the capacity threshold of all the configure sectors that we are going to create, which are not, which doesn't, well, don't exist nowadays, of course, because all these building blocks combinations led to the creation, in particular in Madrid ACC, over 1,000 configure sectors we have. So yes, they develop a methodology to estimate based on how capacity thresholds are were obtained for the sectors we have nowadays, to extrapolate that computation and obtain the capacity thresholds of all these new configured sectors, but it are mostly based on the workload of the sectors.
Thank you. Another question. So, how often are reconfiguration expected to occur?
Okay, so it depends on the input we gave to the algorithm. In this case, if you choose a time interval of 3 hours and you give data every half an hour, the algorithm will give 6 different configurations. So as we mentioned as future work, one of our lines of research would be to try to have into account in the second configuration proposed which configuration was set in the first time interval. So in this case, sometimes maybe the change of configuration won't be as good as keeping the same configuration for a larger period of time. So yeah, the reconfigurations are set with the input data given, but the consideration of the previous configuration to decide if whether it change it or not is one of our next lines of research.
So another question from Sebastian Wagnick. I hope I pronounce well. I see that you adapted the sectorization only once per hour. Any particular reason?
Well, in fact, that was because with operational staff from an area, we saw that they usually make or try to use the optimizer, our optimizer, to see changes every hour. The time interval is always can be changed, and the our framework will compute any time interval you may want. Usually, the smallest one should be 20 minutes because a change of configuration that lasts less than 20 minutes doesn't make sense. But yes, you can change this hour and make just one configuration every 30 minutes or every hour and a half, or as you want. That depends on the request we send to our framework.
Thank you. Another question from Konstantinos. Is there in your study any assessment of the performance and how could be affected performance area of safety, as it could be probably conflict to the one of capacity and also the two environment?
Okay. With regard to safety, in fact, as I mentioned, this optimizer was used in solution 44. And in fact, validation activities for XSS1 were in the past 2 weeks. And we tested the configurations the framework proposed, and we'll compare them with the configuration that was open those days. And to measure the safety impact of the new configurations, we plan to run the reference configuration and the solution configuration and see the potential or conflicts they are in both situations, so we can compare if the new configuration reduces this number of potential conflicts.
Thank you. Are there any questions?
No more questions in WOVA, Daniel.
No more. So I have a few of them, a few questions, because I see that you optimize some transition scheme, but do you expect to include, or perhaps you have already in your algorithm, a transition cost? Because transitioning from one configuration to another one may have a cost different depending on what the pair of configuration you address.
Yes, that's it. As I mentioned here in answer to one question, we received feedback from in-area operational staff, and they in fact remarked this fact because, as you say, sometimes this transition cost is greater than the cost we will gain with the new configuration. So it doesn't make sense to change the configuration. So yes, our idea is to include some method or some model to try to measure this transition cost. The challenge is to make a model to try to take to a mathematical field the subjective reasons that maybe controllers decide why they should change from one configuration to another. Because as we talked with in-area staff, they explained us why these changes are accepted or not, and these are not like very mathematical reasons. So the challenge would be to try to transform these subjective ideas to a real mathematical model in order to include it in the algorithm.
And, in the configuration catalog, do you consider all the options, or do you restrict to a subset of configuration which are more operationally correct, if I can say?
No, at the beginning we didn't restrict any configuration. In fact, we don't really know the number of configurations that the algorithm computes because the combinations are done by the algorithm. But we observed how, as we run the algorithm, the same configurations appeared. Usually here in Madrid ACC, what we saw is that the current CAT at flight level 345 is normally took to a higher level at flight level 365 or 375. So even we didn't restrict the configurations obtained, the algorithm usually, as the air traffic is similar, usually gives the same configurations, and it takes off the CAT, higher in order to take aircraft from the higher levels sectors to the lower sectors.
So another question I have in mind, if you are in configuration A and you can shift on configuration B and C, and B and C have the same cost from the objective you just showed, I think it would be valuable to consider a kind of, I don't know, machine learning approach for having a kind of preferences from the operational people. Because for this objective, I think it is not for the machine. It's the same performance, but for the controller it may be different because you can't include all the things, all the operational stuff in the model. But you expect to play with this kind of machine learning?
Yeah. Okay. Thank you. Yes. In fact, yeah, it's a very good idea to include machine learning techniques to try to simulate what controllers will do to choose the best configuration. Yeah. Thank you.
No, thank you to you. Is there not other question in the chat?
I see there are hands raised, but I don't know.
Please, Pams, help me to open the mic for this person. I don't know.
I asked Milan to unmute himself.
Okay.
Sorry.
Do you hear me? Do you hear? Yes. Okay. Very interesting presentation, and also based on the question, very challenging to ask many questions about things. Actually, you mentioned optimal dynamic airspace configuration, but it's not clear what are you optimizing. Are you optimizing the use of space? Are you optimizing the capacity of space? Are you optimizing both, or you are optimizing air traffic controllers workload? That's one thing. Another thing is what capacity you consider and you have in mind. Is it the capacity of passing aircraft through the airspace or sector, what you like to call it, or it is the capacity is measured by the number of aircraft at the same time under frequency of air traffic controllers. A dynamic changing the airspace under jurisdiction, I don't know how it will be acceptable, and if you do that frequently, how it will be acceptable for air traffic controllers. Could you comment or discuss a few words about it?
Okay, thank you. For the first question, what we are trying to optimize is the allocation of the airspace, meaning the configuration plan of the airspace, in which we are based to optimize it in controllers workload, which we consider that this controllers workload is related to occupancy counts. That's why we use this metric. Okay, so we are optimizing the allocation of the airspace, how we make the order of this airspace, basing on controllers workload, and to measure controllers workload, we used occupancy counts. Okay, then as capacity, we understand it as the number of flights entering an airspace volume, in our case, each configure sectors, for an hour, okay, which is this metric hourly entry counts. Okay, for the capacity threshold was compared to the hourly entry counts at each time to see if these of the configure sectors exceeded this threshold or not. And the third question, the changes of configuration. Okay. Yes, in fact, in the validation activities we performed these 2 last weeks, in the feedback obtained from the controllers, we asked them to give us their opinion in the changes, in the configuration changes, and how that impacted the effort they need to take in their controlling activities. So we are trying to, now we are analyzing the feedback we received, and we'll try to see if these changes were impacted too much their workload, or it wasn't, it was a similar impact as the changes they have nowadays.
Okay, thanks very much. Thank you.
Thank you.
If there are not other questions to keep on
Yes,
schedule, I
Carol
propose to.
Gotts.
Sorry?
Carol Gotts, I see that there's a
Yes.
hand raised.
Okay,
Hi.
so I propose to stop this. Thank you for the presentation. It is very interesting, Florencia. And I propose to shift to the next presenter. So it will be comment. Yes, but I think we shift to the next. You can see each other after for this comment to present, Sebastian. So the next presentation will be given by 2 people. Nikola, I hope you are. It is Radosav who will give the talk finally.
Yes, it's Radosav.
Oh, sorry, because there is a last minute change because Nikola, unfortunately, is not in good shape. I'm sorry for him. So I hope he will recover soon. And so the presentation will be given by two persons. So Arne Strauss, I hope I will pronounce well, professor at the WHU Otto Bernstein School of Management. He's holding the chair of Demand Management and Sustainable Transport at this university. His research is on linking optimization technique to influence demand with transportation planning. Even if you do not present, I give also the short bio of Nikola. Nikola is a researcher at University of Belgrade, Faculty of Transport and Traffic Engineering. His major research interest is in the field of air traffic flow and capacity management. He is actually involved in the SESAR research from 2014 and was the team member of Saturn and Cocta project. Oh, yes, sorry. I see the screen. And so unfortunately, will not be able to present. So Radoslav Javanovich will present instead of him. Radoslav is associate professor at the same university. Is educated at the University of Belgrade, so diploma engineer and PhD, both in air transportation and traffic engineering, and also at the University of Westminster, who did a master in transportation planning and management. He is a leader of 2 undergraduate and 1 postgraduate course at the University of Belgrade. Radoslav was a coordinator and principal investigator of the Jane's 2018 Innovation Award winning project, Cocta, and is presently the coordinator of the SESAR Year 4 project Cadenza, and the UB team leader in the SESAR Knowledge Transfer Network Engage. Sorry for this long introduction, but I think it is good to give also some introduction of Nikola. So I let you the floor, guys, so they will give us a presentation about the strategic cross-border capacity planning and uncertainty.
Yes. Thank you, Daniel. Can you hear me well? Okay.
Stop my micro, but it's okay. Yes, it's okay. You can.
Thank you. Okay, so good afternoon, everybody. And yeah, it was a last-minute change. So Nikola, using the air traffic control jargon, called in sick. So I had to jump in on a fairly short notice. But anyway, I hope I'll be able to replace him. Good enough. This will be a presentation jointly with Professor Arne Strauss from WHO. So Arne is actually running the slides, and he will jump in and after a couple of minutes of my introduction. The paper here is Strategic Cross-Border Capacity Planning and Uncertainty, which was developed in the course of this Cadenza project, which was already mentioned by Danielle. This is, you can see the consortium on this first slide. So other than University of Belgrade and WHO, it's Hochschule Worms, it's Eurocontrol, and the UPC Catalonia. So Arne, next slide, please. Yeah, the Cadenza research is actually, the Cadenza project is an acronym for Advanced Capacity and Demand Management for European Network Performance Optimization. So it's pretty much self-explanatory what we are trying to do based on the project title. It has to do with the mismatch between capacity and demand and painful and costly consequences that problem has for the airspace users and the network as a whole. So you see here some of the indications of this problem. For instance, the ATFM delays, which have been recurring and most of the time increasing before COVID. So 2018 was the peak in terms of the magnitude of those delays. The issue is that the demand is quite variable for a number of reasons, which I don't have too much time to discuss now, whereas capacity is on the other side, or the capacity practices across European landscape are overall relatively rigid. So between this variability or unpredictability of demand and rigidity of capacity, there is a mismatch, which is very costly and painful for the users, as I already said. In Cadenza, we are trying to further improve some of the methods and models which we were originally developing in Cocta project, and try to come up with some new. So by acting actually simultaneously on 3 levers. So by trying to impact capacity in time and in space, and also on the demand side. So moving demand in time in terms of ground departure slots, as already the case today in Europe, and also by moving demand in space. So trying to do some smart and intelligent and network-oriented actions on both sides of the inequality in order to come up with an outcome that is more acceptable in terms of network performance. The goal of Cadenza, as you can see, is actually to try to define and evaluate a number of options for the demand capacity balancing with an aim of improving overall network performance measured in a couple of areas. So using the Single European Sky key performance areas, first of all, probably capacity and cost efficiency, but also, and we will mention this today as well, environment, while keeping the safety undeteriorated, so at least as good as it is now. So more details on this to come. Next slide, please, Arne. Yeah, so I already mentioned that we are working on both capacity side and on demand side. And to do so, there are a number of options. So on capacity management side, we have this flexibility in time in terms of for instance, shifts that air traffic controllers are taking. This can be more or less flexible or rigid, and it could more or less good compared to the demand profile, which is actually one of the big problems. Flexibility in space actually means providing capacity where needed, and there's of course an option to combine the two. And in terms of demand management, there are administrative measures, economic measures, and the mix of those two, so hybrid ones. Administrative measures, I mean, it's perhaps too tough term, but the ATFM slot regulations, which we currently have, is some kind of centrally managed administrative measure. Economic incentives on the other side are trying to play with the prices and offer some incentives to users to behave in a manner which is more acceptable or better for the network as a whole. And then hybrid would be a combination of the two. And then in terms of scope, we have local oriented, we have network oriented. So depending on how wide we want to go, or something in between. This is the geographical scope, and then the temporal scope. Those measures can focus on strategic phase, on pre-tactical, which means several days before the day of operation, and tactical, which is on the day of operation. So what we are going to present today is actually this combination. Thank you, Arne. So the work presented today is just one combination of those various possibilities. So dealing with flexibility in space, meaning this something similar to capacity on demand concept introduced by the Airspace architecture study, and the cross-border capacity provision, which has been mentioned already for a couple of years now, and with some initial actually a nice practical implementation, for instance, between Finland and Estonia. The measures would be administrative, which we discussed today. So, I mean, I would argue that this is more hybrid than administrative, but nevertheless, you will see that we are trying to plan the capacities network-wide by a central planner. You can call it a network manager or a central body or whatever, trying to optimize the performance of the network as a whole and focusing on the strategic stage, meaning up from 7 days up to 6 months before the day of operation. Next slide, please, Arne. Okay, so now over to Arne for some formalization. We can't hear you, Arne.
Can you hear me now? Okay, I can hear myself now, so at least it seems to work somehow. Okay, so what I just was going to say is that talking a little bit about the model, about the way that we formalized indeed this concept so as to try to get some quantitative insights. And the way that we did it was to draw on inventory theory, so specifically to cast the problem into the shape of a so-called news vendor problem. So this is a very well studied problem in that domain, in as far as that it looks at that basic trade-off between making a decision right now and incurring a certain cost for that. So that's then our inventory decision, and the resulting consequences for the future, which of course are uncertain. So specifically in our case here, we can in principle cast the problem into this shape where we're seeking to minimize the overall cost that arises from making, first of all, a decision regarding what is the actual capacity that we would like to plan for. So that's in this case a vector of sector hours. That's what we chose as a representation of capacity. That of course incurs a certain cost. So basically this gamma times h, that is representative of the immediate cost that we are incurring right now. But then this expectation that we've got in the formula, that is then that future uncertain cost. So namely, this will depend on the materialization of all those uncertainties, like how many flights are going to appear and what type of flights are appearing and so on and so forth. Whether there might be disruptions regarding the capacity provision, all the kind of things like that. And that expectation is then being taken over basically those uncertainties, which of course will also mean that there is no way of exactly writing down what that expectation actually is. Coming back to that in a second. That expectation specifically then looks at the future cost arising from that decision. So meaning the displacement cost in terms of rerouting flights, delaying flights, right? So and specifically, given that we have made a decision H in terms of how much capacity to have for that particular time interval that we're planning for, so be that a day or whatever that is, that so upon observing what actually we are facing in terms of the actual materialization of traffic, etc., so everything contained in S, if we are then optimizing our decisions regarding how to configure the airspace and how also to assign specific flights to routes, that we are then obtaining this as the minimum displacement cost. Okay, and that in itself is already a difficult problem, even if we know already what that future scenario is going to look like. And of course, forming then an expectation over that already rather difficult problem is a bit challenging, which is why we chose to go for a so-called sample average approach. So we are, instead of trying to kind of formalizing that expectation, we are simply looking at a set of what the future might be looking like. So essentially we are drawing some distributions so as to create different scenarios as K, and then form an average over those. So that still is difficult because that evaluation of this cost function in the future, this G function that I just showed you, this is rather expensive indeed. And as such, we are drawing on an approach of ours, in fact, that we had, that recently got published in Transportation Science, specifically with the idea of, first of all, creating those samples, right? So those capital K many samples of what the future might be looking like. Then in step 2, to come up with the best budget, essentially, in the sense of that, looking at each of those scenarios individually, to say, okay, if I knew already that this is the scenario that I'm going to end with, what would have been my best decision in terms of the capacity to be ordered, right? And accordingly, from that process, we are getting a whole range of solutions, so namely capital K many solutions, and according to a certain heuristic rule that we proposed in that paper, we're then selecting that specific, that specific decision vector. So this approach we took and adapted that so as to be able to handle this this cross-border capacity provision. And effectively, it's actually very simple because we can simply take that approach as it is and simply define or redefine what a configuration means. So I show that in the next slide. In terms of the actual assumption that underpins this, it's being assumed to be a central pool of cross-border capacity that we're drawing from. So then just very briefly as my final slide on this actual evaluation of that cost function. So knowing already what is my future scenario going to be looking like, That's what we've got over here. So specifically, we're deciding on flight to route assignments. We're deciding on the configuration over time. Right? So A is the airspace, C is a configuration, U is a period of time, such as half an hour, for instance. So we're also deciding on this. Of course, in every time period, in every airspace, there needs to be one configuration, exactly one available. We need to assign every flight to one particular route. And we need to obey certain capacity constraints that result from our decisions regarding that configuration. So, and then finally, we are seeking to minimize this cost. And since this problem is still rather challenging, what we have been doing is to break this up using Bender's decomposition, which actually works quite nicely because the resulting sub-problems are just linear programs that we can solve. And specifically here, this cost factor that would then depend on that particular configuration that we're choosing, which might represent a situation where at least certain sectors are being remotely controlled and as such come with a different cost than if it would have been provided within that same airspace. Right, back to Radoslav.
Okay, thank you, Arne. Yeah, so we developed this model, and which Arne just described briefly, and then we tested it obviously on a numerical case study, which we designed. So it's a relatively small scale. You see on the left-hand side there includes 8 ANSPs in West and Central Europe. So it starts from Poland and Slovakia, I think, in the east, up to Maastricht, I think, in the west. There are 15 area control centers or sector groups, and there's a limited set of configurations which we defined in advance using some historical data on how often they are used. So it's not unlimited. It's or not very big. It's very computationally expensive actually to have a large number of configurations. In terms of traffic, we had something like 1,400 flights, out of which about 1,200 were scheduled flights, which is something like we all have in reality. So about 80 to 85% of traffic is scheduled traffic, and then the rest is revealed at a shorter notice to capacity providers. So we're trying to somehow replicate this proportion. And then you can see on the right-hand side as well that each of those flights had a number of options for its route actually, and those options differ in space and in time. In space, so there are lateral deviations from or reroutings from the preferred or shortest route, and also vertical. And in time, there are possibilities of at-gate ground delays as a demand management measure. Next slide, please, Arne. Yeah, so the results very briefly, testing a number of these, unsurprisingly, or perhaps intuitively, this is what we expected or were hoping for. So in total, there is a reduction of cost when the cross-border capacity provision is enabled in comparison to the scenarios when there is no cross-border capacity provision. In terms of some quantitative results, you see at the bottom of this slide that the more risk-averse policies, or those that are taking lower chance that what they actually ordered or what we ordered or what the network manager ordered in terms of capacity will not be good enough. So such policies with lower risk are actually, of course, doing better on average, and you see that improvement reaches something close to 40% in terms of this EPS 1 policy, which is the most risk-averse one, and still on something like 25% when we compare these EPS 20. This is the first and intuitive result that actually this sort of cross-border provision, or enabling it with a central pool of cross-border capacity provision, and I think we didn't mention this so far, with the fairly conservative assumption in terms of this cost, unit cost of this cross-border capacity. So we assume that this cost is of, for instance, adding one sector hour to some, or borrowing one sector hour to some other airspace is as expensive as the most expensive ACC or NSP in this sample. So since the Maastricht was the most expensive one, we tested it and saying, okay, it's not the idea that we swap the expensive with inexpensive, but let's see what happens if we are very conservative about this. Next slide, please, Arne. Another finding which gives some further insight is actually that, again, expectedly, the cross-border capacity provision, given this cost assumption, which I just explained, increases the cost of capacity provision, which you can see that this green little green dots are slightly to the right when you compare them to the red ones. So green is with the cross-border, red is without cross-border. So it's certainly more expensive to provide some capacity cross-border under our assumptions, but this increase in capacity is much more than offset by the reduction in terms of delay and rerouting cost, which we sometimes call the displacement cost. So this is what the vertical line is suggesting. So if you have a look at EPS1 policy, for instance, you see that it increases the cost by some, I don't know, 15 or 20,000 euros in this case, but it reduces the cost of reroutings and flight delays by more than, I don't know, 80 or 90,000. So overall, the net effect is very positive. And not only that cost efficiency is improved, but also there are, by providing cross-border capacity, we have more direct routing. So the excess distance compared to the excess distance flown compared to the shortest route is much reduced compared to the case when we don't have the cross-border in force. And not only that, we also have a much or significantly reduced number of flights which have longer delays. So this again gives us some further belief in this concept as a whole. To conclude, yeah, I mean, this has already been said. It's a small scale case study. We are working on a larger one, and not only increasing the size of this case study, scaling it up, but also testing the stochastic solution approach. And there's already been some very nice progress in this one, which we presented in Madrid a month ago at the World ATM Congress, and are continuing to develop this approach. Except for this central pool of cross-border capacity, we are also testing cases or scenarios with regional cross-border capacity provision. So in terms that you have couples of airspaces which could provide capacity to each other under certain assumptions. And yeah, so that's medium to large case studies I already mentioned. So I think this leads us to the last slide. And I thank you all for the attention, and looking forward to seeing your questions and answering them.
Thank you both for this nice presentation. I'm going back to the audience to know if there are some questions. Feel free to use the chat.
Yeah.
No question?
Yeah, there are a couple of questions from Sebastian.
I do not see, but feel free to raise your hand or.
Okay, if you allow me, I can do it. Yeah,
you can read the question if you want.
The first one, chronological, is this different from your reference to, which I don't know by heart. Does your work consider that only a subset of all? I hear echo. Daniel, can you mute yourself? Sorry, I think, okay, thank you. That only a subset of all possible combination of elementary sectors into controlled sectors are operationally feasible. Yes, yeah. So we were not just randomly picking up the sector configurations, but making sure that they are mutually compatible so that they can transit from the one, for example, with 6 sectors to the other one with 7 sectors. For we are aware that not all the combinations of sector configurations are compatible with each other, if I understand the questions correctly, Sebastian. And then one more. Yeah. At cost can't simply just control any sector. They need quite some per sector training. For an alien ASP, it seems quite a costly exercise to train their at cost to control sectors a foreign NSP just in case. Does your cost model consider it? Yeah. So I mean, this is of course the fact which we are aware of. We cannot be extremely detailed when modeling the cost, but this is why we were on a very I would argue conservative side when assuming the cost of controlling different sectors. So I mean, you saw the scope of the case study, and Eastern European, Western European countries, anybody who is going to provide the service to a different sector would be as expensive, at least, as the most expensive one, which is MUAC in this case. And we also tested one more expensive solution, actually, or assumption. So adding another 10% on top of MUAC's cost, and it also yielded benefits in terms of performance. So there are more details in the paper, but yes, I hope I addressed this question okay.
Are there any other questions from the audience? I do not see.
There is one of Milan.
Milan is again asking the question. First, compliments for the good presentation and interesting approach, but the question is about intention is that Eurocontrol is to unify the airspace and capacity and flows and these kind of things. How much differences in this cross-border capacities are in order to justify application of your approach? Are there significant differences? In which part of the airspace are these differences in order to make this kind of, let's say, capacity management while passing from one sector to another? For example, you mentioned several countries and airspace of the several countries. How big differences are there in order to justify what you have just been dealing with? Could you? This is just to have a word about.
Yeah. Thank you, Milan. Yeah, I got it. Yeah, well, it's a question which is a little bit more operational than I'm comfortable to answer quantitatively, but qualitatively we are aware of these differences, and we are actually trying to include this sort of reasoning when we are trying to with this regional case studies or regional scenarios for cross-border capacity provision. To deal with, try to find countries, for instance, which are using at least the same provider. So I don't know, Thales with Thales and so on and so forth. So similar interface, if there is such thing, which have comparable levels of traffic complexity and so on and so forth. So this is, I don't have my hands fully into this matter, but there are people from the team who are dealing with this in a very detailed fashion. And I think one of our next papers, probably in next year, will be including some more detail on this matter.
Thank you, and success in continuing your research.
Thank you, Milan.
Thanks.
No other question?
There's another from
Sebastian. One from Sebastian.
Yes, he disagrees.
I did not see. Is it from this presentation or the previous one?
It begins with sorry. It begins with sorry.
No, I do not see.
I can read it. Allow me. Yeah.
Sorry.
Okay, thank you. Yeah, so Sebastian disagrees with our cost assumption. I mean, yeah, we are open for inputs here, and we are having actually a lot of discussion within the consortium and including our expert panel, which also includes a number of ANSPs and EDCOs. So yeah, I mean, this is what we assume in this case study. It could be that we should try with higher increase over MUAC's unit cost. So I mean, thank you for the comment, and it's something which we'll have in mind.
Just a question from me. When I saw your alternate route, how did you generate option for the route from the radar tracks, from an algorithm? How do you propose choice with different routes, if I can say, not similar?
Okay, so Nikola will be very valuable here, but I will try to reply anyway. I think we were using Nest. It was already a couple of years ago, so this data set is from 2016, and I think we were using Nest and trying to generate routes which are different enough mutually so that they don't cross the same sectors, because otherwise it doesn't make many sense. So vertically, laterally, and then of course in the time dimension, it's not that complicated.
Are there any other questions? If not, I propose to thank all the presenters for this virtual session, which is not easy. It's much better when we are all together, but next time I hope it will be the case. Thank you also for the audience to attend these meetings. I wish you a nice evening, because I think it is the last session for the day. Bye-bye.